Hey guys, my name is Daniel. I'm here from the Challenger Learning Center. Thank you for joining us for the Ask a Scientist portion of our activities that we have. Today we're going to be asking a meteorologist. Wonder why? Well, I'm a meteorologist. I went to Florida State University and I got my bachelor's and my master's in meteorology. And ever since I was a kid, I've always had a strong passion for all things weather. My parents tell me all the time that even as a 3-year-old, I would sit and watch the Weather Channel, and when the local forecasts would come on, back then they had the blue theme screen back then, and I would always say blue, 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 and I would bounce back and forth with the songs that they would play during the local forecast. And really ever since then, all through school, weather has been my main passion. I've always loved it. I love learning more about it, how it happens, how it works, all the factors that go into it, and then sharing that passion with people like you. And of course, keeping the public safe. Safety is number one. That is why meteorologists do what they do. They are here to keep people safe, and that includes you guys as well. So hopefully this time that we have some of my passion will rub off on you guys, and who knows, some of you guys might be meteorologists one day. I don't know, we'll see. But yeah, that is why I'm in the field that I am, and I'm so excited that I get to spend this time with you guys to share my passion and to share some really interesting things. We also I have some questions here to answer for you guys, but feel free after or during this time, feel free to add any questions in the comments part of this post, and me or someone at the Challenger will get back with you guys and answer all those questions that you guys have. So ask away, have fun with it, and let's dive right on into our question. So my first question here is, what is meteorology? What is all that about? Let me go and share a screen for you guys. There you go. Okay, so what is meteorology? Well, meteorology is basically the study of any atmospheric process, anything that involves atmospheric physics, chemistry, you name it. But all the meteorology aspects focus on weather and weather forecasting. So some people have approached me and said, you know, do you study meteors or whatever? Because there is meteor in the name. Well, no, there's no meteors involved in the study of meteorology. It's all weather. Okay, so there is a difference in the fields there. So just wanted to make that clear, of course. But so yeah, we focus on all things weather. It's really a fun field. We'll get into it more, but there's a lot of things that go into making a simple weather forecast, much more than what meets the eye, and it's very tricky. Weather is very tricky because so many factors play a role in what actually happens and what we see here at the surface. So that is meteorology. I hope that clears that up for you guys. Question number 2 is, what causes weather that we see here on Earth? Well, let me go to the next slide. The uneven heating of the Earth's surface plays such a big role. So heat, of course, comes from the sun. All that reaches the Earth, but it reaches all that heat reaches the Earth at different angles, and therefore that plays a role in the temperatures that we see and ultimately what weather that we see where we are on the globe. So this diagram at the top of your screen shows, of course, the sun and the heat being transferred from the sun to the Earth. On the left, you have the Earth. Well, on the left and right, both, the Earth is tilted at 23.5 degrees. And whatever season that we're in is all dependent on which hemisphere is tilted toward the sun. So on the left, we are in the summer. So the northern hemisphere is tilted toward the sun and gets more of those direct rays. The southern hemisphere is tilted away, so they don't get quite the direct rays of the sun. Therefore, the northern is in summer, southern hemisphere is in winter. And it flips, of course, during winter. The northern hemisphere is tilted away from the sun, and the southern is pointed or tilted toward the sun. And that is how we get our seasons. And in between, of course, is spring and fall. So just based on this diagram, you can see that the equator regions get more of a direct angle of the sunlight. You can see that at the bottom left of your screen. You can see the palm trees, so that's your tropics. You get more of that vertical, straight down, more intense sunlight, and therefore the tropics are typically warmer than the poles, of course. In the middle, you have your middle latitude, so about 30 degrees or so, maybe 30 to 40. So that's points of, here to maybe the northeast or so. Those places get more of an angle of the sunlight. In general, it's not so much like the tropics where it's straight down. And then, of course, the poles on the far right, on the bottom, you get even more of an angle of the sunlight that comes in and reaches the ground. So because of all this uneven heating of the Earth's surface, you have motion that happens in the atmosphere because, in general, warm air wants to rise, cold air sinks because of all the density differences, warm air being less dense than cold air. And that motion causes all the weather that we see. And think of the atmosphere like a fluid. Think of it like a river, sort of. My professor, one of them that I had at FSU, he really emphasized, think about the atmosphere being in motion all the time, because weather is always changing, the atmosphere is always changing, it's constantly moving. There's so many factors that play a role in what weather that we see. And this transfer of heat that we see from the sun to the earth is uneven based on where you are on the globe, and that causes the weather that we see. And like I said, the polar regions are typically, colder than the tropics, and that is due to the uneven heating of the Earth's surface. And then it falls somewhere in between, kind of where we are on the globe. So that is basically what causes weather. And of course, this also involves our seasons that we see as well, and I talked about that as well. So hopefully that clears that up. Next question is, what's the difference between weather versus climate? That's such a good question because those two can easily get mixed up and confused at times. So this next graphic should clear this up for you. So on the left, we have the definition or the descriptions of what weather is. It's a short-term state of the atmosphere. So it's what's happening right now. It's right now in time and not over a period of time. Of course, weather can vary from time to time or location to location, just where you are on the globe, but it always includes a time and a location at a particular moment in time in a particular spot, okay? Climate, on the other hand, is a long-term pattern of weather. So it's basically weather over a long period of time, and typically that period of time is about 30 years or more. Look at it like an average weather pattern over many years from one place, okay? So that's weather versus climate. Big differences, but yet very important to understand what the differences between them are. Next question that I have from you guys is, what are the various precipitation types? We're going to jump into precipitation now. There's many precipitation types that we can see, and it's interesting to see how those happen, because it's not just it's not just, oh, we have rain or we have snow. Why do we have those conditions, and why might we not? So this diagram shows our precipitation types on the left. I just want you to focus on the leftmost diagram here. So this is a vertical profile, basically a slice through the atmosphere from the clouds to the ground. The clouds are on the top of the diagram. Try to match up with your view of me right here. And then at the bottom is the ground, okay? From left to right, we have rain, freezing rain, sleet, and then snows on the far right. So in general, precipitation falls from a cloud as snow. A little fun fact that one of my professors said is down here, at least, in the south, it doesn't snow much, right? So the closest blizzard that we have to us is right above us a few miles up. So that's pretty cool, right? So right above us in clouds, you have ice, you have snowflakes, you have all sorts of winter precipitation that we would see it, but it's above us in clouds. So from the clouds, you have snowflakes falling, and then that temperature profile or that temperature pattern that happens from the cloud base to the surface plays the role in what type of precipitation that we see here at the ground. This is what makes forecasting so tricky, because especially for like winter precipitation and stuff like that, it's hard to tell all that might go on in the atmosphere a few days out. I mean, we're basically forecasting not just at the surface, but above us and how that might change. And it's crazy, right? One thing changes and that can swing the whole forecast to something else. So let's start with rain. So yes, you have your snowflakes falling from the cloud, but then you have warm air. This orange region is warm air above freezing. Okay, so just focus on the leftmost column of the of this diagram. And so you have the snowflakes falling into air that's above freezing, and it's above freezing all the way to the ground. So the snowflakes melt and they stay melted, pretty much raindrops, all the way to the ground. And that's what you see at the ground. That's what we would see here on the ground. So that's rain. Freezing rain's a little different. So of course you start out with your snowflakes, goes to rain that melts, but that warm air doesn't reach all the way to the ground. There's a little shallow or a small portion of cold air or below freezing air right above the ground. So the rain falls, but it doesn't have time to completely refreeze before it hits the ground. But it freezes on contact. When it hits that ground, it can freeze, or it will freeze on contact. And that's how you get black ice and thick ice on tree branches. And that's very dangerous. When you're driving, power can go out with power lines down, trees down, branches falling, all that stuff. Because of the ice, it can weigh on that. So that's freezing rain. That's how that happens. Sleet is even more different than that. So of course you have your snowflakes, they melt, but then you have a large depth of below freezing air right above the ground. So the rain has time to refreeze. Now, when it refreezes, it can't refreeze into a snowflake. It just can't work that way. So when it refreezes, it forms little balls of ice or ice pellets is a way of looking at it. And then those hit the ground, and that's what's known as sleet. Okay. If you've seen some pictures of sleet, if it's it can kind of look like snow if it covers the ground completely, but you know, when you look at it in a closer view, it's definitely the little balls of ice. So very neat stuff there. And then snow, of course, is when the air is completely below freezing or about freezing from the cloud to the ground, and it doesn't melt on the way down. So that is your difference in precipitation types: rain, freezing rain, sleet, and snow. So hopefully that helps you guys out if you were ever unclear about that. And let's see. So that leads us to our precipitation down here in the south. I have a couple questions for you guys, including the next question is, what does, if you see it in a weather forecast, okay, we have a 60% chance of rain on Friday or whatever it might be. What does that 60% mean? So I have a quiz question for you guys. So for example, what does 30% chance of rain mean? Is it A, 30% probability that it will rain in one location? Is it B, that we have a 30% chance of it raining in many locations? Or is it C, 30% of rain in a large coverage area? Give you guys just a minute to think about that. Very different in our choices here, but think about that very carefully. And I'm going to reveal the answer. Here we go. So for those of you who said A, you're correct. Congratulations to you guys. 30% chance of rain means that it's a 30% probability or a 30% chance that it will rain in one location. It's by location. Okay, it's not a 30% chance of it raining, or a 30% chance of rain over an area like C would. That means that it's like of the entire region, 30% of that area will get rain. That's not that. It means in your location where you are, at that pinpoint spot that you are, you have a 30% chance of receiving rain. Okay? So it's not by distance, it's by your one location. So make sure that you understand that. Very, very important. Okay, now the next question is a very interesting one. How do we get snow in the South? Or in particular, how do we get snow here in Florida? I know it doesn't happen much, but it can happen. And I get so excited when we have snow in the forecast because you don't see that too much. So 2 things have to occur. My very first meteorology class, my professor shared with us the 2 conditions that we need here in Tallahassee for it to snow here, okay? And this next graphic will show it to you on the left. It's a weather map of what happened back in February 12th of 2010. This shows you the 2 conditions that we need. 1, you need a strong Arctic push of very, very cold air that invades the South, okay? You need temperatures to be below freezing over a long period of time to help, to help cool down the entire atmosphere, the air, and even potentially the ground if you want to have snow to actually stick. Okay, so you need a very strong Arctic push, very, very cold air. After that cold air is in place, then you need some sort of precipitation. And that precipitation, as you can see on the left, there is a low pressure in the Gulf that moved through. You need a low pressure system or a weather system that moves to our south. And that would pretty much mean it in the Gulf because there's not much to our south besides the Gulf, of course. So you would need 1, that Arctic push of cold air, and 2, that low pressure or that weather system to bring in the precipitation. And because you have the below freezing temperatures, as we showed with the 4 types of precipitation, then you would have either snow or some kind of precipitation that is wintry type, either freezing rain, sleet, but it all depends, again, on that vertical profile, what happens above us, as we showed before. Very, very tricky forecast for that too. And that's very tricky to try to make a call on that. But we have forecasting models that we use as guidance, and we have a lot of tools that we can use to help make as sound and as hopefully as much of a confident forecast that we can make for keeping you guys safe. And this weather system on February 12th, 2010 actually produced on the right, you can see the snowfall amounts even into the panhandle of Florida. They had maybe an inch or 2 of snow. I don't think us in Tallahassee had any during this system. I do see a 1/4 of an inch in southern Georgia, but I don't think we had much here. But we have had our chance and our opportunities of seeing snow. If you guys remember, 2 years ago, January 2018, we had a pretty potent winter storm move through. And here in town, we broke all sorts of records. We had a whopping 1/10 of an inch of snow, woo! But that broke all sorts of records. And because we just don't have snow here. So that measly, well, not really measly, but that was a big thing. That 1/10 of an inch was a big deal, and that broke all sorts of records here. Areas to our west or to our east near Lake City had a lot of ice, and they had greater or more than 1/4 of an inch. That I'm sure caused a lot of power being out, a lot of trees down. I'm sure, because that's a lot of ice, especially for down here. Down here, that's a big deal. And then in southern Georgia, they had some areas receive over 3 inches. So this was a big storm. And even though we only got the 1/10 of an inch, that was a big deal. And we had a scene like this. This is the view from downtown. We actually had snowfall. This is off of Mike Seidel's Twitter page. He shared this video. This is just a screenshot of it though, but this shows snow falling downtown Tallahassee, getting snow. That is huge. And again, we got the trace of an inch at the airport, and that broke all sorts of records. Really, really big deal. Very, very exciting. I love this. I remember this day and got so excited. It was great. So yeah, we've had a few other times. I think back in 2014, we had the ice day, and we had some sleet during that time. But again, all that all what, whatever goes on above us plays that role into what we see here at the surface. And forecasting that stuff, that's tricky business. So that's your precipitation. That's how we get snow down here. I did want to jump into, I believe severe weather is up next. Yes. And I'll get to a couple questions in here, but before I do want to go over the basics here of severe weather. A forecast, of course, I did want to start off with that. It's just like a 5-day forecast, 3 to 5 day forecast that you would see on the news, on the Weather Channel. Potentially severe weather, it might be predicted, but that's totally different from a watch and a warning. Before a watch is issued, you want to make sure that you are always prepared in case something like that is sent out and something does happen. So make sure that you have your kits ready, your emergency kit ready. We'll talk about that at the end of this time with you guys, but make sure that you have your things ready to go before a watch and a warning is issued. So that's what a forecast is. It's just like a 3 to 5 day regular forecast that you would see on TV, online, or whatever. A watch, when that is issued, either for a severe thunderstorm watch or a tornado watch or a hurricane watch or whatever it is, primarily for severe weather or for severe thunderstorms and a tornado watch, I want to focus on those. Conditions are favorable for severe weather, okay? Then storms are expected to form soon or are already forming. Make sure to be weather ready and ready to take action if a watch is issued, especially if a warning is issued, meaning that severe weather is occurring or is imminent at your location. You need to take action right then. Do not delay, take action, and prepare. And well, you should be prepared at that time, but you should be taking action at that time. Very, very important. So that's your difference between forecast, watch, and warning. So thunderstorms. I did want to show you this before we get to our next question. I believe it's on the next slide. These thunderstorms are associated with colliding air masses. So you know what a cold front, we have warm fronts. I'm sure you've heard of cold fronts and warm fronts and stuff. So a cold front is a boundary between two different air masses, typically a warm and moist air mass, and behind the cold front you have a colder and a drier air mass. Well, you have these two very different air masses literally clashing with each other, okay? And we talked about warm air, since it's less dense, it rises, cold air sinks, of course, but this warm air, it rises, and it has nowhere to go but up, and the cold air, of course, can't go into the ground, so the cold air goes under the warm air and forces that warm air even up more, and then this clashing, because of this boundary between the two air masses, forms your thunderstorms that we typically have with cold fronts. You can see on the right, on the top right, or on the top left, shows how a cold front advances with the warm air retreating and the warm air rising, and then all your storms on the boundary. On the right, you can see that actually happening with the cold front behind those main thunderstorms. And then on the bottom, you don't need to worry about too many things here, because there's a lot of terms here that I'm sure will go over your heads, but I did want to show you the basic diagram of a thunderstorm. You have your warm updrafts, meaning like your air that rushes up inside the storm. You have your cold downdrafts, the air that moves down. This helps the storm to breathe. And as long as those stay very strong and healthy, you have a developing and healthy storm. And then, of course, your precipitation below the cloud base there. As a reminder, I did want to say that this slide and the upcoming slides are slides that we use all the time at the Challenger for our extreme weather learning lab. So this is what we share with the kids, and I'm excited that I get to share this with you guys too. So that leads us to our next question. So we have our thunderstorm structure. We know what they're associated with. Our next question is, what causes thunder? Let me see, I believe, actually, no, before that question, does hail form in cold or warm air? We're going to get to that, and then we're going to get to thunder in just a minute. Thunder and lightning is up next. But hail, does hail form in cold or warm air? What do you guys think? Think about when thunderstorms typically occur. Do they typically occur during warmer weather, or is it colder weather, like during the winter, during the spring, summer, fall? Well, typically the stronger storms are with the changing of the seasons and changing of temperatures, of course. So that's usually spring and fall. And then, of course, you have your all your summertime storms too. But typically the main outbreaks occur during the spring and the fall because you have your more clashing air masses with things changing, with the tilt of the earth and the seasons changing, all that good stuff. So in general, hail forms during warmer weather, and because that's when you have your strong storms with your changing seasons and whatnot. So how hail forms, you have your strong updrafts. Those are your blue arrows in the middle of the storm that we showed on the previous slide too. It's very cold aloft, meaning way above at the top of the cloud, or within the cloud. It's very, very cold. We're very below freezing. Okay, this freezes those water droplets within the cloud, and they get pushed up because of that of the updraft. And when they freeze, think of like a jawbreaker. Okay, so it has different layers, right? And as the water droplets freeze and they get pushed up, they can fall due to gravity, but then they can get pushed up again because of the strong updraft. If the updraft is stronger than the gravity pulling it down, it can keep on rising, fall, rise, fall, rise, fall, and every time it rises, it helps to refreeze again, right? And it develops these core layers that keep on growing and growing and growing. More water gets on there, it freezes, and it just grows and grows and grows. And that's how your hail, as it shows here, gets larger and larger. And we'll show how large they actually get. And as we said, the strong uplift keeps the ice airborne until gravity takes over. Then the ice falls out and that hail hits the ground at whatever size it ends up being. The stronger the updraft, typically the larger the hailstone. And take a look at this. These are your hail sizes. So you have pea-size hail on the left. That's about your 1/4 inch or so. Penny-size hail is about 3/4 of an inch. Quarter, if it's the size of a quarter, you have an inch hail. Ping pong ball size hail is 1.5 inches. Golf balls, 1 3/4 inches. Tennis balls, 2.5 inches. Baseball, 2 3/4 inches. It even gets bigger than that. Softball, 4 inches. And then you have a grapefruit size hail, 4.5 inches. That's huge, right? Think about, that's a falling chunk of ice, and you do not want to be outside if it starts to hail. This could do a lot of damage to homes, cars, even trees and shrubs and stuff. If you're talking about multiple softball hailstones falling out of the sky, that's not good, right? So definitely take shelter if ever a warning is issued, because hail could always be associated with a severe thunderstorm warning, of course, or a tornado warning as well. All that can be one-on-one with the same storm. So that is hail right there. Those are your different hail sizes. Pretty interesting stuff for sure. So that's hail, and I believe we're going to move on to thunderstorms. Yes, okay. So here's your lightning. We're going to be talking about lightning and thunder. Our next question is what causes thunder, and we're actually going to get to that after this slide. But before we do, I did want to talk about weather safety for lightning. When thunder roars, go indoors. That's the saying. Very, very important that you remember that. When thunder roars, go indoors. Lightning fatalities is huge. You can see on the left for outdoor sports. This is just outdoor sports. For soccer, 40%. This is from the National Weather Service. 3% for football. Golf is 27%. It's a huge thing. So if you see lightning or hear thunder, you need to get inside immediately. You also need to seek shelter in an enclosed building or a car, something or someplace that will keep you safe. And then we need to wait at least 30 minutes after hearing the last thunderclap to return outside, okay? Because if there's still thunder, that means there's lightning somewhere. Very important that 30-minute threshold is followed. It might be tempting to go outside if you don't hear anything for like 10 minutes, but you need to wait, okay? Little fun fact that we talked in some of my meteorology classes. There have been times that it's been blue sky and there's been a lightning strike. Wonder why? Well, the way lightning behaves It can be kind of have a mind of its own, and lightning can travel, and it can kind of go out. Instead of going down from the storm cloud, it can actually go out and then eventually land outside, kind of outside the storm. And where you are, it looks like it's blue sky because you're outside the storm. Lightning can still travel. So that's a big deal why they want you to wait 30 minutes, make sure that storm is a safe distance away, and that you do not hear thunder for at least 30 minutes before you go outside. So to answer our question, what causes thunder? This should give you a hint right here. Lightning is hotter than the surface of the sun. Think about that for a minute. So down here in the southeast, the hottest it can get, maybe 100, 105. I think the hottest temperature in I don't know if it's the globe, or at least the US, was in Death Valley. I think it's 134 Fahrenheit. So that's a lot more than the hottest temperatures that we find here on Earth, right? Hotter than the surface of the sun. That's huge. So what do you think would cause thunder? Well, I'll give you the reasoning here. So you have that instant lightning with its associated heat, very, very high heat, 50,000 degrees Fahrenheit, being emitted into the air, into the atmosphere. That sudden addition of heat, just with physics, how that works, it causes air to expand. And because of the rapid expansion in the atmosphere, that expansion causes sound. And that sound is the thunder roar or thunderclap that we hear after lightning, because lightning has to occur for that heat to be added to the atmosphere quickly, and then that causes the expansion of the air and therefore the thunder. So whenever there is thunder, there is lightning. They go hand in hand, but lightning occurs first and then thunder follows. Okay, so that is what causes thunder. Little added note, I did want to give you guys something to try at home next time you experience a thunderstorm. There is a way of telling or kind of estimating how far away the storm is, or how far the lightning strike was that you may not have seen, but you definitely heard the thunder with it. Okay, so after you see, after you see a lightning strike, even if it's a distance away, count the number of seconds between that lightning strike that you see and when you hear the thunder. Okay, so for every 5 seconds that you count, that means that the storm is 1 mile away. Okay, so basically what you need to do is add up your total number of seconds that you count between the lightning and the thunder, divide that time by 5, okay, and that gives you the total number of miles away that the storm is at from where you are. Okay, very, very interesting thing. So if you guys get to do that, make sure to share with us. We have all of the comments to add to that, so feel free to add that to our comment section. We love to hear from you. Okay, let me see. I believe we have more severe weather. Yep. Okay, so flooding is something that might not be covered as thoroughly as some things should be. It's not one that we really think about too much, to be honest. But it's very important that we try to emphasize. Meteorologists really need, we work on emphasizing flooding, because it's something that, we don't really think about. We just don't. When you see a flooded roadway, turn around, don't drown, right in the middle of that slide. Turn around, don't drown. Look at this, 6 inches of fast moving water. So 6 inches of fast moving water can knock over and carry away an adult. That's huge, right? 12 inches, a foot of fast moving water can carry away a small car. Holy cow, that's crazy, right? 18 to 24 inches, so 2 feet or a foot and a half to 2 feet, fast moving water can carry away most large SUVs, vans, and trucks. So don't even try to drive through that, because you don't know how deep the water is, and just a little bit can carry you off and you might be done. Okay, flooding, I believe, is the #1 fatality causer of all severe weather, so it kills the most people. So keep that in mind. When you see floods, turn around, don't drown. Just don't do it. Okay. Let's move on to tornadoes and hurricanes. Tornadoes are large vortices or spinning columns of air that touch down from clouds and reach the ground. They can cause a lot of destruction. But seeing them on radar is very interesting. We have the tools to be able to tell if a tornado is on the ground. So you're seeing right here 3 images from a radar that you would see on the news or the Weather Channel. This is called radar reflectivity. It's the basic radar tool that we use that shows how strong the rain is, and you can kind of get a feel for how strong the precipitation is. But you can also see a debris ball, which is the white circles on your screen. That is like your main tornado vortex, your main circulation of the tornado itself. And you can see it moving through time. I believe that's a time lapse, I'm pretty sure, of this particular tornado. I don't know which one it is. But we as meteorologists, we need to make sure that before we ever see this on the radar, that we have issued warnings and that we know that we have warned people and that they are taking cover. I'm going to skip this hurricane section for just 1 minute. I'm going to go to the next slide just for a minute to show this. Okay, this is another tornado signature on radar. So reflectivity is on the top right. Base velocity or velocity is on the top right, and correlation coefficients on the bottom left. Those are the 3 I want you guys to focus on. Okay, reflectivity, of course, is the regular radar signature that we usually see on the news or on the Weather Channel. I'm going to try to draw on the, let's see if I can get this working, on the velocity. Give me a second, let me find this. Okay, here we go. So I'm going to go into a little tangent here, but this is really fascinating. So on the right, you see from radar. So your radar, those radar ball, like the golf ball things that you see at the airport, those are your radar. Okay, that constantly scans the atmosphere at different angles and views, and sees what's going on. The green on here, well, actually, let me say this first. So on the right side of the velocity image with the reds and the greens, it says from radar. So the radar is somewhere over here. I'm going to draw an X for most likely the radar is off the screen here, but just pretend that it's right here, just for a visual case here. Now the greens here mean that it's showing motion or velocity toward, or things that are moving toward the radar. So I'm going to draw a arrow here toward the radar. Okay, so the greens are moving toward the radar, the reds are moving away from the radar, like this. Okay, now if right here in this middle area right here, right in the middle where they collide right there, that's a very strong couplet of differing velocities of moving either away from the radar or toward the radar. And you can see here that we can kind of form a circulation here. Look at this. Isn't that cool? So you can see the circulation here that's formed from your velocity pattern. Greens, of course, toward the radar, reds away, and that strong couplet is where your tornado signature is. Okay. To further verify that a tornado is on the ground, we use correlation coefficient. This in the lower left hand corner, and this basically shows the uniformity, or the size pattern of objects that the radar is seeing. If it's near 100%, meaning that it's pretty much the reds, it means that the particles that it's seeing are pretty much uniform. So rain droplets are about the same size as they fall from the sky, right? So in general, if it's raining, your correlation coefficient, or your CC in this case, would be about 100%, meaning that it's 100% uniform. Now, look at this area right here. I'm going to draw a circle right here. Right here, there's a blue kind of signature blue pinhole here with values of like 55 to 60%. Okay, I'm going to actually clear these drawings so you can see it better. This means that there are objects of differing sizes flying through the atmosphere. Okay, and that means that's a signature of a debris ball, meaning that debris of different sizes is flying through the atmosphere. And you do not, as meteorologists, you do not want to see that until after a warning is issued. Because if you see this and a warning's not issued, that means we've failed, and that would not be good because people's lives are on the line, and you got to get those warnings out immediately. So this blue area means that trucks, maybe trees, or parts of houses or cars are flying through the atmosphere because they're not the same size as a regular raindrop. So that's the signature for a debris ball. That's further confirmation that a tornado is on the ground. Let me go ahead and exit out of this. Okay, I'm gonna go back up to, hopefully that enlightens you guys quite a bit. The Weather Channel, if you ever watched them during a severe weather outlook or a severe weather outbreak, they've been really touching on these different radar, radar components, and they really show what we look at to see different things that are happening in real time. It's huge, the tools that we have. Not only do we have all the radar tools, we have the computer models, we have a lot of things that we can use to try our best to keep the public safe. Safety is number one, as I said before, very crucial here. Okay, I think one of our final topics is about hurricanes. We all know them very well down here, of course. They're big spiraling systems that form over the oceans due to a lot of evaporation, favorable winds. These systems are vertically stacked like a sandwich. Think about that. And if they're not stacked, if there's a lot of wind shear, a lot of strong winds aloft, that might blow the storms off to the side like this, it's not stacked as well, right? And that weakens the storm usually, and it could even die off too, depending on how strong the shear is. So you definitely need the right ocean temperatures. Typically, I think the magic threshold is about 26 to 27 degrees Celsius of water ocean temperatures, which I think is about upper 70s to around 80 degrees Fahrenheit. That's usually good for formation of a system to eventually become a tropical storm, hurricane, or whatnot. So that's typically the threshold for that. In general, they do not typically result in an overwhelming amount of thunderstorms. Granted, the stronger storms can get lightning in the core and the eye wall around the eye, and some of the outer bands do have storms in them. But overall, and as a wide viewpoint of these storms, thunderstorms are not in abundance. Okay. One thing I did want to mention, comparing tornadoes and hurricanes on this slide, tornadoes can get up to 300 plus miles per hour. That's your EF5, meaning the enhanced Fujita scale that we use. I'm not really going to go into that too much. Hurricanes use the Saffir-Simpson scale. That's your category 1 through 5. And hurricanes can get over 200 miles per hour, which is pretty impressive. Think about the impact, though, of tornadoes versus hurricanes. Both are very, very dangerous to life, of course. But to compare the distance differences. So a tornado, mile wide, moving through an area. It varies based on how long it lives, of course. But I mean, you can talk about many miles, but a mile across as it goes through. Hurricanes, you're talking hundreds of miles wide, and those can cause even wide impacts far apart from the center. Little tidbit, the cone of uncertainty, the forecast cone that they show, don't focus on the middle of the cone. This is a very important thing that I want to stress to you guys. Don't focus on the middle of the cone, because that's just where we think that the eye is going to go. But since these are huge storms and huge systems, it can impact people far out from the actual cone itself. Plus, I believe the statistic is that there's a 33% chance that the storm might not even stay in the cone. It could go out of the cone. So sometimes hurricanes can have a mind of their own, and they can be very tricky to forecast for sure. So that is tornadoes, that's hurricanes. let's go on to safety tips for both. Tornadoes. You definitely want to go, if a tornado warning is issued, you want to go in the lowest floor, most interior room of your shelter, wherever you are. That means find a hallway, find a bathroom, find a closet, find a basement, okay? Away from windows. Do not be at near windows because things could go flying through the window and hurt you. Definitely want to cover your head. Use blankets, use a helmet. I know that might seem odd, but use a helmet, use a pillow, use a mattress, whatever you have on hand, cover those heads. Very important. And evacuate mobile homes as much as possible. They are not safe during a tornado, okay? So those are your basic safety tips for a tornado. For a hurricane, to stay safe during a hurricane, don't be by a window like this guy is. Just don't do that. But you need to have a disaster kit. We'll talk about what's in the disaster kit on the next slide. Evacuate if necessary. If necessary is the key, okay? Don't just leave town because you just want to. Because that could clog the roads, that could prevent other people who desperately need to leave from getting out of harm's way. So only evacuate if necessary. You can also fill your bathtub with water in case you need it for a later time, in case you lose power or don't have any water left after the storm. Definitely stay inside, turn off major appliances, make a meeting plan, fill up your gas tanks, okay? There's a lot of things that you should do before the storm hits. And even the sooner the better, because once those forecasts come out, you know, everyone wants to go get the same stuff and they need to, but make sure that you plan ahead, okay? Very important. So my final question is, what do we include in a disaster or an emergency kit, okay? This is from the National Weather Service. These are your must-haves on the top right for an emergency kit. You need a first aid kit, of course, phone and a charger. Make sure to charge them before the storm. Know a weather radio. Have a weather radio, some way to get warnings. Have bottled water on hand. Have non-perishable food, including canned goods, but non-perishable. Okay. Have a flashlight. Have batteries. Have a whistle, even if you need to signal for help afterwards. Additional supplies are on the bottom right. Extra baby food, cash, important records. Get your documents. Okay. Set them aside. Have them in a safe spot. Pet items for your pets. Fire extinguisher might not be a bad idea. Change of clothes for a couple of days just in case power's out and you need them and you need to leave or whatever. Have books and games, things to keep you guys busy during the aftermath of a storm or during it. But the main thing is to be prepared in advance. Okay, safety is number one. Even, you know, what you guys do for yourselves and what we do to help with the forecast and keeping you guys safe, it all goes hand in hand. Safety, plain and simple, is number one, and it has to be. Okay, I think that covers all of our questions. I'm just going to look over my question list that I have, and I believe that is everything. As I said before, make sure to drop any additional questions in our comment section, and either I or someone at the Challenger will get back with you and answer your questions. Please let us know about what you're wondering about, any question. Drop it down there, and we will let you know an answer for that. I look forward to hearing from you guys. I hope you guys learned a lot, and hopefully some of my passion kind of rubbed off on you guys, and hopefully, you know, you guys have a passion for the weather too. Maybe I've sparked an interest in some of you as well. And who knows, some of you might become meteorologists like me one day. So thank you guys for joining me, and I look forward to hearing all of your questions. I will catch you guys later.